Hi, this is Mr. Beck. This is a lesson on double slit interference, which introduces Young's equation. And this is your social distance learning lesson for today. If we take a look at a point source of waves, a stone thrown in a pond, a laser, a loudspeaker, anything like that, it's going to create a series of waves that extend in every direction. And in this case, the blue is marking the crests and the white is marking the troughs. So you can see the crests and troughs forming from that point source. Now we're only going to be looking at one edge of that point source. So if we take the point source and we see the waves coming out, what we're going to do is initially send them through a single slit. What we're going to see here is a pattern of diffraction. And the diffraction is when the wave passes through a single slit, that point here on the single slit is going to act like a point source itself. So what you would see is you would see a new set of waves coming from that new point source, and those would extend out into the distance. If instead we send that wave through a double slit, what's going to happen is each one of those slits is going to act as its own point source, and so we're going to get that pattern, that diffraction pattern from each one of those point sources, creating waves of its own. So here would be a pattern of diffraction from the top slit, and this pattern of refraction comes from the bottom slit. Now, anywhere a crest is going to meet a crest, we're going to find constructive interference at this point, at this point, at this point, at this point. Those are going to be constructive interference where the waves are going to add up. So you're going to have a crest meeting, or a wave like that meeting up with another wave, and those two waves are going to add up to a bigger wave when the crest meets the crest, and to a smaller wave when the trough meets a trough. But we've got a period of crest, trough, crest, trough. So along that line, we're going to get constructive interference. Other points are going to be where a crest meets a trough, and a trough meets a crest, and a crest meets a trough, and a trough meets a crest, and so on. And along that line, we're going to have destructive interference where the crests are meeting troughs and the troughs are meeting crests. And so we're going to get very small waves there. Now, if we take a look at a screen, if we allow that pattern to project onto a distant screen, then we want to know what's going to happen at a certain point on that screen. So let's take a look and extend just the waves that are going to reach that point on the screen. What we would see is there is a set of waves. There's a path of the light from, in this case, light from the top slit, and a path of that light from the bottom slit, and they're going to meet at a certain point on the screen. Of course, we could have picked any point on the screen and seen what happened there, but let's just look at this point right here. Now, if it is the case where those two waves arrive in phase, where the crests are meeting crests and the troughs are meeting troughs, so here crest meeting crest, here trough meeting trough, what those are going to do is they're going to add together constructive interference to make a bigger wave, and so that point on the screen will result in a bright spot. However, if those waves were to arrive out of phase, then I would have crest meeting trough and trough meeting crest and crest meeting trough, and those are going to cancel out, and so I'm going to get a dark spot if that were the case. Now, what's going to determine whether it's bright spot or dark spot? If we take a look, we can set up some geometry, and we're going to set this as the angle from, theta here is going to be the angle from the center path between, straight line path between those two slits. And then it's going to measure an angle up to where I would be looking on a screen. Now, if we look at both of those waves and we look at them coming out, we can see that here the waves are going to be in phase because this original point source is going to be equal distance from those two slits. So it's going to start in phase, and then those waves are going to propagate out from each slit with a certain wavelength here for each wave. Now we can draw another triangle down here where this distance is going to be some number of wavelengths, and this is going to be the distance between the slits. So the when we get to the point over here, I could measure the distance all the way to the top slit, and I could measure the distance all the way to the bottom slit. And you can see that they would be the same, the same, the same, the same until I got to that last little triangle. And so this is going to be the difference in the length of the path from the double slits to that point on the screen. So that's why we call it the path length difference. And that's what's going to matter, because since it's a single wavelength of light, then the distance can be defined in terms of number of wavelengths. And so the difference in the length of the path from each slit to the screen, that path length difference can be measured as a certain number of wavelengths. Here, let me hide my screen for a second here. So the path length difference is going to be some number of wavelengths, and so we're going to write that as some number of lambda wavelengths. Now, we also have the distance between the slits is d. So we've got three variables we're defining here. D is the slit separation, the distance between the slits. Lambda is going to be the wavelength, and theta the angle from the original direction of the beam. Now you can see that we have a sine theta relationship between the number of wavelengths and the distance between the slits, because this is going to be a right triangle that I could draw a little right triangle sign right here. And so therefore, for that right triangle, the number of wavelengths is going to be the opposite side, and then the distance is going to be the hypotenuse. So the sine of theta is going to be some number of wavelengths divided by the distance. That's the sine of theta. So now, if the number of wavelengths is exactly 0 or 1 or 2 or 3, it would be 0 right here in the middle. Then the waves are going to arrive in phase. If that distance is off by exactly one wavelength, which I've drawn here, that exactly one wavelength would mean that they would be arriving in phase again up here. So if I have exactly one wavelength or two wavelengths or three wavelengths, then I'm going to wind up with a bright spot up there on the screen because I have exactly that many number of wavelengths and I'm back to in phase. Now you'll hear the term order. So there's first order, second order, third order, and then it'll be bright or dark. But the bright would be the maximum. And so in this case, if the number of wavelengths equals 0, we call that the 0th order maximum. If the number of wavelengths equals 1, that's the first order. And if the number of wavelengths equals 2, then that'd be the second order maximum. So you'll hear that term order, first order, second order, also 0th order. So the 0th order corresponds to that central bright fringe. So we'll use m to determine, we'll use m as the variable that we call order. So if m equals 1, it'd be the first order. If m equals 2, it'd be the second order. So instead of this number symbol up here, the hashtag, we're going to replace it with m. So we can write down that the sine of theta equals m lambda divided by d. So this is m lambda, that's some number of wavelengths, that's what we determined here, and then d being the separation of the slits. Then if we multiply by d, we get to the equation d sine theta equals m lambda. So this is a simplification of that sine definition, and d sine theta equals m lambda is an equation on your equation sheet that will help you find the angle given the other variables or vice versa. So now we can write d sine theta equals m lambda and put that up here as a equation that we're going to use. So again, when we have a bright fringe, m is going to be 0, 1, 2, or 3, 0 in the center, and then the first bright fringe out here when m equals 1, and the second bright fringe further up when m equals 2. So again, m equals the order. If we're talking about dark fringes, in order to see a dark fringe, what we would have to have is the path length difference be a half wavelength or 1.5 or 2.5, so that the waves would arrive out of phase. So again, if we measured the distance from this point to this screen versus that point to, the other slit, then we would have a 1-to-1 match for every wavelength all to the right. But we would only have this little bit here that we would be measuring the difference in the length. So again, path length difference. If that was exactly half a wavelength, then they'd arrive out of phase and it would be dark. Or if it was 1.5 wavelengths, if that distance there was 1.5 wavelengths, again, it would arrive out of phase and be dark. So the conditions for dark are going to be where m equals a half, or 1.5, or 2.5, or 3.5, and so on. Now, some textbooks, most textbooks would actually give you a different equation to use for bright and dark, but I just like to do it this way. So you might get some pushback from your professor, but it won't mess you up on the AP exam. But the conditions for dark is where m is a half or 1.5, 2.5, and so on. But be careful that the first dark fringe is also called the 0th order dark fringe. The second dark fringe away from the center would be called the first order dark fringe. So when m equals 1.5, that's going to be the first order dark fringe, but it is the second dark fringe. So be careful about that. Know that the first one happens at a half. So here's an example problem. Let's say we heard that a 540 nanometer laser shines on two slits separated by 0.25 millimeters. Now, if I heard you yelling, "Stop at me," that's good. So a 540 nanometer laser, what is that? Well, that is going to be the wavelength of that laser. So I can write that lambda equals 540 nanometers. If I write 540 nanometers, remember that nano means times 10 to the minus ninth. These sorts of problems are going to be a little confusing because they'll give you nanometers in one place, they'll give you millimeters somewhere else, they'll give you meters somewhere else. So the easiest way to pull those all together is just to use the exponents. So here I have, instead of nanometers, I have 540 times 10 to the minus ninth meters. Don't worry that that's not in proper scientific notation. Don't try to make it 5.40 because you won't know if it's 10 to the minus 987 or 10 to the minus 9, 10, 11. So it's easiest just to leave it in the times 10 to the minus 9 for nanometer format. It's separated, the slits are separated by 0.25 millimeters. That's going to be D, the slit separation. So I can write D is 0.25 millimeters, or 0.25 times 10 to the minus 3 meters. And then I'm looking for at what angle would the second dark fringe be found. So second dark fringe, what that tells me is that m is going to be 1.5 because the first dark fringe is going to appear at 0.5. The second dark fringe would happen at 1.5. So now I can go ahead and pull up my equation. And I'm going to use d sine theta equals m lambda. I can substitute my values, 0.25 times 10 to the minus 3 meters for d, then sine theta equals m, which is 1.5 times lambda, 540 times 10 to the minus 9. If I continue and rearrange that equation, I can have sine theta equals 1.5 times 540 times 10 to the minus 9 divided by 0.25 times 10 to the minus 3. Notice that those were both in meters, so the meters is going to cancel out. So that gives me the sine theta is 3.24 times 10 to the minus 3. And if I do an inverse sine on that, I would get 0.186 degrees. Now there's another equation that we need to use all the time when we're doing double slit. And so I'm going to derive that equation now. We still have our triangle that is representing the path from the double slit off to, let's say, that distant screen, that we get an angle between the central bright fringe and where I'm going to find something of interest. So I've got the slit separation, the wavelength, and the angle from the original direction of the beam. But now I'm also going to add x, the distance from that central bright fringe to whatever I'm interested in happening up on the screen. So that's going to be x. When I put a screen there, I'm going to have x, that distance from the central bright off to some point of interest. So x is the distance from the central bright fringe. You'll often hear it written that way. I'm going to introduce L prime, which is the distance from the fringes, which will be generally really close together, so I don't actually need two triangles, but the distance from the fringes off to that point that I'm interested, that x. So I can define sine theta on the small triangle with m lambda being the opposite over here, divided by d, the hypotenuse of that triangle. And then on the big triangle, I can do the same thing and say that the sine theta is going to be x divided by L prime, opposite over hypotenuse. So in both of those cases, I have sine theta equals m lambda over d, and I have sine theta equals x over L prime. And the theta in the top triangle and the theta in the bottom triangle, hopefully you can see that those two are going to be the same because as I increase the top triangle width, if I were to take the top triangle and bring this and make it bigger, you see that this would also get bigger. And so you can imagine also if this were to close down to 0, then this one would close down and these would be, the m lambda would shrink down to 0 because I would have no path length difference up to that point. So since those triangles are similar, what I can do is I can take the sine thetas and set them equal to one another. So that means that the x over L prime here is going to equal the m lambda d from over here. So I can have x over L prime equals m lambda divided by d. Now, what we're usually given is the distance to the screen, which is L, which is not quite L prime, but for a small angle, you might notice that L and L prime are going to be pretty close to one another. And so what we have is the x over L is going to be almost equal to m lambda over d. So we have something called the small angle approximation, which generally will say that the sine of theta and the tangent of theta are close enough if the angle is small. Now, when we're dealing with, if we want, say, a 1% error between the sine theta and tangent of theta, I think that if we keep it within, I believe it's 7 degrees, then if that angle theta is 7 degrees or less, then I'm going to be off by less than 1%. So we very often can use this small angle approximation where the distance to the screen and the distance to the point on the screen that I'm interested up there are going to be basically the same. So with that small angle approximation, I can get to the equation x divided by L instead of L prime equals m lambda over d. And if I take that equation and I multiply both sides by L, I get to a new equation that you'll find on the equation sheet, x equals m lambda L over d. So the distance that I'm going to find something interesting, the distance from the central bright fringe, equals m, that order number that we were talking about, whether it is 1, 2, 3 for bright fringes or a half, 1.5, 2.5 for dark fringes, lambda the wavelength, L the distance to the screen, divided by d the distance between the slits. So now I have a new equation that I can use in order to calculate double slit interference patterns. So I'm going to add that to my equations up here. And so now I have two equations, d sine theta equals m lambda and x equals m lambda L over d, both of which you should find on a handy equation sheet. Let's take a look at a sample problem using that second equation. A 370 nanometer laser, 370 nanometers, that is going to be the wavelength of the laser. So let me write lambda equals 370 nanometers, or 370 times 10 to the minus 9th meters. Again, we're given nanometers and millimeters and meters all in the same problem, so it's easiest to write the numbers using the exponents. So lambda is 370 nanometers. Now it shines on two slits separated by 0.15 millimeters. So that's the slit separation d. So we write d equals 0.15 millimeters, or 0.15 times 10 to the minus 3 meters. Again, keeping everything in meters is going to be useful. It's projected on a screen 2.4 meters away. So that is the length, that is L, the distance between the slits and the screen, so we call that the screen distance, is 2.4 meters. That's already in meters. Now it says, at what distance from the central bright fringe would the third bright fringe be found? Third bright fringe, the center is 0, so the first is 1, the second is 2, the third is 3, so we write m equals 3 for the third bright fringe. And we're looking for what distance, so that's going to be x equals question mark at this point. So now the equation that we use to relate all those variables is x equals m lambda L over d, and we're looking for x, so we don't need to rearrange that. So we can substitute m, we have 3. For lambda, it's 370 times 10 to the minus 9th meters, times L, 2.4 meters, and we're divided by d, which is 0.15 times 10 to the minus 3 meters. Now, if you look at the units, we have no units, we have meters, and we're dividing by meters, so my final answer will come up in meters. Doing the math, we get x equals 0.0178 meters, or you could look at that as 1.78 centimeters. So I hope that was useful to you, and look forward to seeing you here on the next video. But take some notes, and we'll see you next time.